Hold on, huh? One moment. Share. Let's see. Sorry, guys. That's okay. I'm just going to do this. Sorry, I'm having a bit of a senior moment now. Please bear with me. Okay. Yeah, it sends it to the other screen. Okay, let's do this. There. I think that's better. Can everyone see the screen okay? Just to check.
Yes, we can see the screen.
Okay, perfect. Thank you very much. Okay, so as I mentioned earlier, thank you again, Ebenezer, for your very kind introduction. I'll be talking today about dynamic simulation and going through some of the problems we've managed to solve using dynamic simulation. And this extends from the design phase all the way up to operations. So let me just run, before that, just run through a quick overview of East 101. Then I'll talk about some of the solutions that we've gone through. Today I'm going to talk a bit about upstream solutions, but what we're doing over here kind of covers both upstream and downstream, oil and gas, as well as like a refining and petchem. And then talk a bit about some of the training that we provide. I think Ebenezer's told everyone that we're planning on going there sometime in the early first quarter next year to run some training classes. I went there. I was very fortunate to have gone there, I think last year. I gave like that class at the university, Kumasi Technical University of Science and Technology. Okay, so just a bit of an overview of East 101. I started this company back in 2003, and we're actually based in a small city outside of Kuala Lumpur, Malaysia. We put Kuala Lumpur there because we're actually in a small city called Shah Alam. But I put Kuala Lumpur there because no one in the world knows where Shah Alam is unless you're from Shah Alam. So we're actually about 30 kilometers away from Kuala Lumpur. And I think from our coordinates, you might be able to guess where we got the name, where we got the company name East 101 from. We've got agents and partners all over the world. So we've got sales and services office in Houston. You've met Ebenezer, and who is from EBL. We've got partners in London, sales agent in Jakarta and Thailand as well for Southeast Asia. So we're a very small company. We're a very small niche company. Again, we focus in primarily simulation-based services. So we've got about 15 engineers, most of us in the team. About 11 of us are process engineers. The rest are sales, as well as support, general office support. Yeah. So our focus areas tend to be within process engineering, particularly process simulation related services. We occasionally do some software development, and we do some machine learning and AI. I like to think that East 101, with our domain expertise, brings some RI into the AI, i.e. some real intelligence to the artificial intelligence. So we do some AI solutions for our customers, but what we bring along is a domain understanding and domain expertise in how facilities are operated and designed. So when we put together our solutions, it's not just doing like, advanced statistics or neural net type of solutions, but we actually bring in some of the engineering understanding underpinning these solutions that AI solutions that we provide. Okay, so just a bit of an overview of some of the work that we do, and you'll see some of these examples very specifically. For the upstream business, we do quite a bit of controls studies for offshore platforms and FPSOs. We've done quite a bit of work for MODEC, and we've done some work back in the day. I guess Tullow was managed by MODEC. We've done a bit of work for the Tullow facility. We've done quite a bit of work for MODEC and the Petrobras in Brazil. So there's a lot of FPSO kind of work that we've been focusing on, and it generally is aligned with controls, particularly compressor surge analysis. So we'll be going through one of those examples later. These are some of the other types of activities that we do: blowdown analysis, heat management, high integrity pressure protection system, or any other kind of instrumented pressure protection systems, heat exchanger tube rupture, water injection, surge type of analyses. Flow assurance is another area that we work in, which is multi-phase transient fluid flow. So this is primarily for multi-phase systems, gas, oil, water transmission pipelines. We take a look at liquid management, slugging, wax management, hydrate management, etc. Yeah. I'm just going to run through this real quick because I don't want this to turn. This isn't. I promise you, this isn't a. It's not a sales pitch. Just wanted to get you up to speed with some of the stuff that we're doing. Operational excellence. One of the things that we've been working on quite a bit is machine learning and AI solutions. So we've come up with some AI solutions to help facilities with controls, process controls, primarily looking at control anomalies, flagging and identifying control anomalies. As you know, when you go into a facility, you might have hundreds or thousands of controllers, and you want to be able to identify potential issues, and you can tell by patterns. If you have, for example, a sticky valve, you have systems where there's a lot of dead time, you have a lot of second order behavior. So as an engineer, as a controls engineer, you can look at that and say, okay, that's anomalous. But try to do that over like several thousand controllers, and it becomes quite a task. So we've put together some AI tools to be able to identify anomalous controllers. And we're going to the next phase where we're looking at coming up with potential root cause analysis to kind of drill down and figure out, what's wrong with some of these issues. So it combines some neural net AI with some physics-based model, as well as some real intelligence, some of our many years of experience designing and operating facilities. And as Ebenezer mentioned earlier, I do a lot of workshops. So we teach, we do in-house classes specifically for companies. Occasionally we do public classes. So that last year I did like a 1-day public class open to everyone in Kumasi University. I also teach in a couple of universities here as an adjunct lecturer. So that's a different kind of stuff. That's a bit more theoretical for students. Yeah, so hopefully if anyone here is interested, please let Ebenezer know. I'd be very looking forward to coming to Ghana again and running some of those classes. I had a great time there, had all the great Ghanaian food, had fufu for the first time. Looking forward to going back, trying out some of that fufu and that nut soup or something. I can't remember. Ebenezer, you guys kept me very well fed with a lot of local delicacies. I'm looking forward to going back and trying that again. So, yeah, I like to say that we are essentially using a lot of our simulation technology to minimize unknowns when we're designing facilities, when we're taking a look at troubleshooting, operating issues. The foundation of a lot of our computations are physics-based simulation models, obviously tempered with our practical engineering knowledge and expertise. One thing I just wanted to push up real quick is this is something that we've been doing very recently. That's carbon capture and storage, CCS. So these are just, if you take a look at all of these kinds of facilities, that's something that people tend to start getting into these days. And we've done quite a bit of CCS for MODEC, carbon injection sequestration. We also did the world's first very large-scale CCS solution for the Petrobras, MODEC Petrobras Tupi facility. We've also done work within Malaysia doing feasibility studies. Most recently, in terms of global activities, we've just finished up a job, I think, middle of the year for US multinational oil company. Again, Petrobras is another organization that we typically do quite a bit of work with. So the type of work that we do for CCS, I'm not sure how big this is in Ghana or the African continent, but we typically look at the compression system, feasibility for detailed design, some operations troubleshooting, as well as transport fluid flow in the pipelines. Yeah. So our expertise is again is from a lot of the experience that we have. When you're dealing with high CO2 systems, the properties become a bit more complex. You can't really use the property packages straight out of the box. You need to be able to evaluate and maybe do some tweaking. We've got some custom tuned property packages that we typically use for CO2. I know these days a lot of people use a GERC 2008, and that's an option as well. But there's pros and cons when you're doing different types of simulation. Yeah. So yeah, that's just a bit of some of the CCS we're doing these days. With regards to the East 101 services across the hydrocarbon supply chain, when I first started my career, I did a lot of work in refining, gas processing, and LNG, petchem. This is back in the 1990s. So you kind of know how old I am. My first job was in the 1990 when I worked for Petronas. When I started East 101 in 2003, I pivoted upstream because I couldn't really get too much work downstream. So that's where we developed a lot of our experience for multi-phase fluid flow and compression. Yeah. And lately, obviously, carbon capture and storage. So today I'll be talking primarily about some of the upstream solutions, but we've actually done quite a lot of work downstream as well. So the AI work that we've done is for a liquefaction facility, and we've done quite a bit of work in design and troubleshooting for refineries within Malaysia, as well as refineries in the US and Canada. This is a brief list of our clients. So you can kind of divide them up into operating companies, engineering companies, and FPSO organizations. Okay, so it's enough of the introduction, and let's talk a bit about some of the engineering and technical work that we do. So today I'll be talking about 5 areas that we typically work on. The first, this is pretty much like our rice bowl. This is where we do a lot of our work in. It's centrifugal compressor surge protection and controls analysis. I'll give you an example of what we do there. Heat exchanger, tube rupture. This is for shell and tube exchangers. I'll be talking about liquid surge and water hammer protection. Blowdown. So I think a lot of times, I think most process engineers here have done some kind of blowdown analysis, either using HYSYS or Unisim blowdown, where you actually have to sum everything up into like one volume and kind of blow down that particular volume. In our case, I'll talk about what we refer to as distributed blowdown, which is having the volumes, the pipes, all the configurations, so you can tell exactly where your cold spots are. And I'll talk about process safety time. This is essentially instrumented pressure control. So that's a typical one that we normally work on is HIPS, or high integrity pressure protection systems, or any other kind of instrumented pressure protection control. Okay. Ebenezer, is everything okay? Can everyone still, can you still see and hear my presentation?
Yeah, everything is okay.
Okay, I'm going to stop periodically and check, because I've had situations where I got connected and then I end up talking to myself for like 15 minutes before I know I'm disconnected. So, okay, the first thing I'd like to talk about is compressor surge protection and controls analysis. And again, all of these types of analyses here are done utilizing some form of a dynamic model. Yeah, not just within HYSYS or Unisim, but other applications as well. And I'll address that as we go one by one through each of these areas. Okay, so what do we mean by compressor surge, centrifugal compressor surge? So this is just like a quick sketch of a typical the first stage of a compression system. And you can see that this consists of you've got piping, you've got like an inlet header, in this case, where you might have a PCV to flare. You've got the inlet scrubber to knock out any liquids, your compressor and driver, aftercooler, outlet SDV, and you normally have like a check valve over here to control, to reduce the volume of reduce your surge volume. Yeah. So what do we mean by surge? Well, in some situation, you might find that the pressure the discharge pressure may go up. Why would it go up? Well, you could have a problem further downstream. Maybe this is feeding to some other processing trains. Maybe some of the trains has tripped. And it has retarded the flow, causing the increased pressure over here. Yeah, could be that maybe there's like an inadvertent closure of a valve. So what happens if there's a sudden reduction or retardation in flow? Your pressure goes up. When your pressure goes up, there's a potential for reverse flow. So there's a potential that your gas, rather than going forward, will want to go back. When it goes back, it starts to pressurize your suction, and after the suction gets pressurized, it goes back to the discharge, vice versa. Yeah, so you'll have this sort of oscillatory flow. Another reason why this could happen is, let's say your inlet flow rate is retarded. Say this is coming from wells and some of the well strip. There would be insufficient flow in the compressor. The insufficient flow in the compressor would also result in this potential issue as well, where you've got like an overwhelming discharge pressure causing like a backflow. Yeah, so this can go back and forth, and this oscillatory behavior can cause mechanical damage. So what do we do in a situation like this? Well, we need to take a look at certain types of analyses to see what sort of situations may bring a system to surge, where a compressor may start approaching surge. One might be startup or shutdown, particularly if you have an emergency shutdown and you kind of like cut the power to your compressor real quick. You might have like sudden variations in demand, like what I said before. There might be you might have like your compressor might be feeding several processing trains. Maybe one train might trip, or some of the trains might reduce in pressure. There might be like a turn down. You might also have a situation where you switch compressors in and out of service if you've got like parallel compressor trains, or you have two trains and one train trips. Now, when the surge happens, it can occur within the order of magnitude of hundredth of a second or milliseconds. So you have to be you have to be careful in making sure that you have some protection in place to prevent this from occurring. Okay, so with regards to the simulation analysis, what we typically look at is we take a look at various types of process upsets. Yeah, like what I'd talked about earlier in the previous slide. And we'll take a look at these particular areas. So within all the things that can happen in a compressor, these 4 items here are typically where you might have a potential surge analysis. So we typically set up a dynamic simulation and define these types of events. You can schedule a bunch of these types of events in any of your flowsheet simulators, HYSYS or Unisim or Petrosim. Yeah, and we take a look at how well the anti-surge or the surge protection system is designed in order to prevent surge or to prevent any kinds of like a high pressure excursion from occurring. Yeah. Okay, so now in order for us to take a look at this, you may be familiar with these compression systems. In order to prevent surge, in order to prevent backflow going through the compressor, what we do is you would have a anti-surge line bypassing the compressor and sending the gas back to the suction so you can maintain the flow, a smooth activity. Now, there's a couple of questions that you need to, that people typically ask at this stage. One is this system here, is the anti-surge valve adequately sized? Is the piping also adequately sized? Yeah. If it's not adequately sized, then do I need to install another valve to allow the flow to come back? So in this case, this is a hot bypass valve. So this valve takes the flow before the aftercooler and sends it back. Why is it important? I'll show you in the next slide why we have hot bypasses. Can I install a hot bypass in order to get more flow back if the individual anti-surge valve is insufficient? It may be sized sufficiently, but it might not be able to open fast enough. And we'll see why that's the case in the next couple of slides. Instead of a hot bypass, maybe I can just have like a piggyback or a cold bypass over here. Yeah. Okay, so earlier I just showed you like a simple schematic, but if I put this in a very simplified GA, a general arrangement drawing, you can see that sometimes if you're offshore, an offshore facility, your equipment might be on different decks. So your suction scrubber might be on one deck, compressor on another deck, and the hot gas from the compressor, your hot discharge has to go up. If it's an air cooler, it's normally going to be at the top deck. So it's going to go all the way up and then come back down again. So you've got a fairly long path. So that's why sometimes you might want to bypass the air cooler and shortcut it with a hot bypass. Yeah. So a lot of times the effectiveness of the anti-surge system or the anti-surge loop is going to be a function of this arrangement as well as all of the piping and valve sizes. Okay, so one of the things that we typically look at in order to determine whether or not we need a bypass is to take a look at a compressor shutdown, an emergency shutdown. Emergency shutdown tends to be the most onerous case because what happens is your compressor is running under normal speed. If it's sudden, you suddenly have, like, say, for example, a trip, say maybe an issue, maybe there's a blockage or a system trip or H2S alarm trip the compressor. If it's a motor-driven compressor, then you essentially turn the motor off and the compressor just winds down based on its inertia very, very, very quickly. And as it winds down, it doesn't have enough head to push against the system head, and the system head overwhelms it. So during the emergency shutdown, that is a potential for surge to happen. And even though you have an anti-surge valve, but because the power cuts off very, very quickly, sometimes the valve can't open enough to give you enough CV to have the flow come back. So you have a backup valve or a fast stop valve, a valve that you can just actuate very quickly, just open it fully in a short period of time to allow the recycle flow to go back. So this is an example for a compressor shutdown. I've got some of the details over here in terms of the suction conditions and the discharge conditions. And initially, the proposed ASV anti-surge valve size is about CV of 350. So we want to know whether this compressor is going to surge during emergency shutdown. So this is the model. This was actually built in a software called VMG Sim, but you can use any kind of simulation tool. It's just like driving a car. Once if you got a good car in your hands, you can drive a Volvo, you can drive a Toyota. They'll all give you the same results in the hands of someone who knows how to drive a car. So we don't really have any preferred software. We'll generally use whatever software the customer tells us to use. If the customer doesn't have any preferences, we'll use whatever we've already paid for. Or if you don't need software, sometimes you can just do a hand calc. So this is a program called VMG Sim. I think now it's called Symmetry. So I've got this compressor, this suction scrubber, compressor, valve, and you can see here I've got aftercooler, and anti-surge valve over here. And I've got all the piping model. So typically when we do these models, they're very rigorous. We've got all the piping configured. And this is the compressor map. You normally get this from the vendor. So we've tried this analysis. If you take a look at this map, this is essentially a multi-speed compressor, and this is the initial operating point. Upon shutdown, you can see it starts to wind down. The speed starts to reduce and the flow starts to reduce accordingly. This red line here is the surge limit line. So what happens is once you go into the surge limit line, you're at risk of the compressor going into surge. You can go, right here, you can go into the negative flow region, go back and forth, and that causes your vibration. So we want to keep it away from this red line. So based on our analysis, we ran the dynamic simulation, and then we tripped the compressor at some point in time, and this is the trajectory. So we've seen that it's entered the surge region. So there's an issue. Also, the time in the surge region is important. Some compressors vendors say you can stay there for like a second or 3 seconds or something, depending on what speed you're at. Some compressor vendors will not give you that, will not allow for that. So it depends on your compressor vendor, your rotating equipment team, etc. So what we've done is now we've put in a cold bypass. So we've added, so in case of, instead of 150 CV, we've added another 170, 350 CV. We've added 170, and we find that in this case, that prevents the compressor from entering the surge region. Yeah. So analyses like these are really important because now you can see a difference. Without the bypass valve, you have a surge, and with the bypass valve, that's able to keep your compressor within the desired operating region as it winds down nicely. So these simulations have essentially allowed us to get some insight and ensure safety and costs as well by making sure that we prevent the compressor from experiencing any potential mechanical damage and vibration. Yeah. Okay. So Ebenezer, is everything okay? Is everyone still, is my audio and visual still up and running?
Everything is perfect. We are with you.
Okay. So this is another compressor study that we've done, and this is for, sorry, the previous case, sorry, I didn't introduce this properly. This case was for was for a design case. So we did this in a detailed design stage for one of our customers. This next example is for an existing facility. Yeah. So it's a compressor controls issue. This one doesn't have anything to do with surge. But what was happening is this is a gas compression module. It's essentially two parallel trains, each with 3 stages: low pressure, intermediate pressure, combine back, go through a glycol dehy, and then into the third stage. This will be going into gas injection and gas lift. Yeah. So one of the problems that they had over here, they saw was there was inconsistent readings for some of these compression trains. So you can see that the flows over here seem to be like imbalanced. Yeah. You've got more flow in one, less flow in another, and the flow rate readings were kind of all over the place over here. So the flows were maldistributed across the compression trains. And one of the compressors was having like a high discharge temperature at this point over here. I think it was going about like the expected discharge temperature should have been about like 140 or so. We were getting up to about like 180, 170 at this point. And at the suction header, even at a low gas throughput, we're getting a lot of flaring taking place. Yeah. Okay. Now, again, we built the simulation model. This was coupled with the offshore site visit. So the engineers went offshore, took a look at some of the setup over there, and made some observations, had some ideas and hypotheses, and came back and tried running through those hypotheses through the simulation model. Yeah. So for the simulation analysis, we had 2 offshore site visits, got a lot of data from Pi, Then we made some observations offshore. Then onshore, we had built the construction. We had built a rigorous dynamic simulation, validated it against the actual design of the facility, and based on that, we can see what the system was designed for and how it was currently performing. So we could use that to identify certain gaps. Yeah. So we performed then an analysis of the observations from the site. We also did a bit of anti-surge analysis, so that wasn't really much of an issue in this particular case. Yeah. So here's a finding that we got. One of the reasons that we had maldistribution between the train was one of the anti-surge valves, even though it showed it was closed, it was actually passing. So we noticed that the discharge of the valve, the piping, there was condensation on the piping, which indicated there's flow because you get a Joule-Thomson effect. Yeah, from a high pressure, low pressure, you start getting it gets cold, and the piping was cold, and that's a bit odd. So we were looking at the system and shot it with a temperature gun. So we're in Malaysia. The temperature is about similar to Ghana. That's one thing I noticed when I went to Ghana. It was the conditions, the humidity was almost exactly the same as Malaysia. So the ambient temperature is going to be in order of magnitude about 30 plus degrees Celsius. But when we shot we took a look at the discharge of the ASV valve, which is supposed to be closed, it was about like 12 degrees Celsius. And there was condensation around it. So we found later that that ASV, that anti-surge valve was passing. So even though the indicator showed that it was closed, it was passing, and it was causing a recycle to occur in one of the trains. So it was retarding the throughput of one train, so there was more throughput going through another train. So that caused a lot of the imbalance. Yeah. And we found that the erosion and fouling, that the valve was passing because there was a lot of corrosion product causing erosion and fouling of the ASVs. Yeah, it was also fouling up the compressors. So because of that, we had because that compressor was in recycle. That's why we saw the other symptom, which was like suction header flaring. And because it was recycle, the recycle caused the suction header to increase in pressure, and we had continuous flaring. Yeah. So we essentially identified the damaged valves to be replaced, sent that out, wrote a report again about the corrosion, and initially the CO2 levels were supposed to have been lower for the system. So the material that was selected, carbon steel, did not have the resiliency to deal with corrosion. So the other solution, unfortunately, albeit a very expensive one, was to change out certain sections to prevent corrosion. Yeah. So this is one of our operations troubleshooting cases. Yeah. Okay. So I see we've got someone's raised their hand, but I think we'll save our questions till the end of the presentation. So I think Ebenezer, if anyone's got a question, just punch it in the chat, and then I'll get to that when we're done. Okay, Ebenezer, are we still okay? You can still hear me and see me?
Yes.
Okay. So the next example I'm going to talk about is a heat exchanger tube rupture, and this is another case that we've done for design. Yeah, for design. This actually is quite an interesting case because it's a design, but it was actually an FPSO which was being redeployed to a new field. So the pressures and compositions were being were different. So the heat exchanger manufacturer wanted to ensure that the position and the location of all of the relief systems on the heat exchanger could address any potential tube rupture situation and could protect the heat exchangers from potential overpressure. So this system is, you'll normally, this heat exchanger tube rupture analysis, you'll normally see this at the high pressure gas areas in the system. Normally, you see it in other areas as well, but a lot of times in the compressor aftercoolers. Yeah. So in this particular system, it was a compressor aftercooler. Okay, so what do we mean by heat exchanger tube rupture? So if we take a look at the schematic of heat exchanger, shell and tube heat exchanger, uh, we typically may expect, and in this case, we've got high pressure gas in the tubes and lower pressure on the shell side. Now, in this particular case, you can typically expect potential failure at the tube sheet over here and potentially at the tube bend. Yeah. So, yeah, and yeah, that's example of a ruptured tube. Now, in our case, we typically assume like a simple guillotine rupture. That's nothing as like a complex as that kind of like a rupture case. A typical guillotine rupture with gas coming up from two different sides of the tube. Okay, so if we take a look at the dynamics of a tube rupture, first thing that happens when you have a rupture, you see a percussive shock. Yeah, that happens. So as soon as it breaks, you've got your high pressure suddenly entering a low pressure system. That percussive shock generally is extremely fast. You have a pressure wave that travels at the speed of sound in whatever liquid that you have. And that percussive shock, that high pressure, is followed by a liquid displacement and later followed through with gas breakthrough. So when you're designing these relief systems, you need to take all of this into account. The fast transient, how fast is this? Can I use uh, a relief valve? Do I need to use a bursting disc, or can I use a buckling pin kind of configuration? So all of those have different transient, different responses associated with that. Yeah? What kind of uh, protection can I use? How big is it, and where do I need to place it? At the inlet, near here or farther down? Where do I need to place this? Yeah. Okay. So first thing we need to know is what's the resulting magnitude, duration of the pressure surge, and also where in the shell does it occur? Yeah. So we want to look at the pressure profile as it traverses the shell. We want to know if this heat exchanger is going to be adequately protected from overpressure. And will this also cause some of the issues with the inlet and outlet piping? Yeah. So what kind of analysis do we need to do with this? Well, we need to do a transient single phase hydraulic computation. And you can't use HYSYS or UNISIM or PETROSIM or symmetry for that because even though it appears that there's some sort of pressure flow interrelationship in dynamic HYSYS, it doesn't include all the momentum balances, the momentum balance component of the Navier-Stokes equation. Yeah. So if you're using HYSYS, UNISIM, symmetry, dynamics, there's only two parts of the Navier-Stokes or Bernoulli equation that's taken into account. One is delta P. Well, actually, the pressure drop driving force, frictional pressure drop. Yeah, the friction, F equals to K squared rho delta P, friction or 1 over friction, which is conductance, and elevation, H rho G, the static head. But it doesn't take into account all of the kinetic energy terms or acceleration terms. So you can't use HYSYS for something like this. You need to use like a single phase tool like PipeNet or AFT impulse. Yeah. So as part of the analysis, then we need to do to figure out what kind of pressure relief system device we need and where the location is. Okay, so here's an example. So what I've got is in this case, I've kind of like modeled this shell and tube exchanger. I've plotted out the profile here, and I'm inducing like a rupture at the inlet. And I'm plotting all these three locations across the exchanger. So one is at the inlet piping, two is at this location, 3, 4, 5, etc. Yeah. So I've got relief valves placed in various locations here as well. So I've got like a bursting disc. Yeah. And this simulation happens very fast. So if you watch this timing, it's happening within less than a second. So let's see if I can run this animation. Yeah. Okay, so I've induced that. You can see the pressure start to move up. and the pressure wave starts propagating across. So it's now the time, it's a really small thing. It's less than a second happening. And you'll see the bursting discs start to lift at some point in time when the pressure reaches that point. Yep, that's lifted, and that's lifted. So now the pressure wave is going back and forth. You can see again the timing. This is less than a second. That's about 1/10 of a second. You can see the wave going, traversing back and forth across this. You can't see this in HYSYS. So you need to use this kind of tool, or you need some kind of like a CFD-like tool. This is, I guess you can consider this like a one-dimensional CFD. So that's a wave that's just gone back and forth, yeah? It's just a single dimensional, just axial computational fluid dynamics. Okay. So this is what we were looking at from this analysis. We had like a buckling ping valve over here, and one located over here. So initially, in terms of the sizes, we're looking at the a 6-inch of, and we found that with the 6-inch system, we had some issues. We were hitting, it was not acceptable. We were actually hitting the, going past the maximum allowable working pressures. In order for us to reduce that, yeah, in order to reduce that, we have to go with an 8-inch valve instead, yeah. So this is also with regards to some of the, if we take a look at the max pressure over here, for 6-inch, we saw the max was about 28, 27. When 8-inch, it was like 20, 22 and 21. MAWP in this case was about 23. Yeah. Okay. Yeah. So what you get again from a dynamic simulation is magnitude and duration. How much and how long is it going to occur? Okay. So these are obviously by having this, we've been able to determine where we have the where we locate these relief devices. And you know, it takes a guesswork out of it, so you can actually manage your capex properly. We also tell you like how far these discs, the relief devices, need to be away from the shell. Yeah. Okay. Ebenezer, we doing okay in terms of visuals and audio?
Yes, I have a question in the chat. I don't know if we would address it or address it after the
Yeah, I think
conversation.
I'll run through everything and then we'll address the questions.
Okay.
Yeah. So the next analysis that we did was like a liquid surge and water hammer case. And this was for a design case. So again, this is not using HYSYS. For something like this, you have to use PipeNet or AFT impulse. Yeah. So we want to know in this case, I've got a pump and a valve, sorry, a pump and a piping system. We want to know whether we're going to get liquid surge occurring during transient events, startup, shutdown, sudden valve closures, etc. If there is a sudden pressure surge, is it going to be significant relative to the essentially pressure rating or the flange rating of the system? So again, we want to know what's going to be the peak pressure relative to your design or hydrotest pressure. Another thing we want to know as well is there any potential risk of cavitation during the transients? Yeah. So when I'm starting out, if I'm starting up the valve, do I have enough NPSH over here to prevent cavitation from happening? I want to make sure I prevent the pressure from dropping below the vapor pressure of the liquid. When you have cavitation, you start getting pump vibrations and you trip typically. Yeah. If there's any kind of pressure surge, are the supports going to be strong enough to withstand the dynamic forces? So in this case, we've done these cases for fire water, produced water, lube oil, LNG loading. So the issue, yeah, you could have like a sudden closure or some kind of transient. Typically, you can use like some hand calcs to figure out if there's going to be an issue, a rule of thumb, to figure out what kind of a pressure increase you're going to have, assuming that you have some information on the speed of sound in that particular liquid and sudden deceleration. So I think a lot of companies will have a lot of spreadsheets, yeah, And that spreadsheet will essentially, I think it's a Joukowsky equation. It'll tell you how fast or slow you need to close a valve. Yeah. And that'll give you like a first pass analysis. But then later, as your system gets more complex, you might want to have a proper hydraulic dynamic hydraulic analysis. So in this particular case, for something a bit more complex, we've got the pump curves, the piping configuration with isometrics, valve data, and we actually shut down the valves, open, close the control valves, switchovers, and things like that. And we take a look at the pressure, potential pressure surges and pressure increases across the system. Yeah. So in some examples, we want to take a look at if you have like a closure, if you want to prevent this system from potentially surging, we take a look at what are some of the limits that we can have on the valve closure. Yeah. If we have like a different valve trim, if you have, say, for example, linear valve versus like equal percentage valve is like, it's opposite of a quick of a quick opening. It's a quick closing valve. Yeah. So in some of the cases, we might have to take a look at the stroke time of the valve. In some cases, we have like an issue. We might have to resize some pipes. So we had like a recent case over here where unfortunately we had to go back to the customer and say that we've got some issue on the sizing. We've got some liquid surge issues. We need to revisit the pipe diameters for certain sections. So what are some of the other separations, some of the other considerations? Sometimes, particularly if you've got like overboard dump valves, which we see in a lot of the offshore facilities, you might get, as the liquid starts to go to the overboard dump, you might get the liquid kind of separating because of the siphoning effect. Yeah. And the siphoning effect might cause essentially vapor pockets to occur. And that could also result in a vapor cavitation on some of the overboard dump valves. Yeah. So I've got a lot of friends who sell valves for a living, and this is something that they're always complaining about, the cavitation on the overboard dump valves. So how do we know what's going to happen? Well, again, we built our simulation using something like PipeNet or AFT Impulse. On PipeNet, you can track cavitation to different degrees of rigor. Yeah. So if you use these kinds of the transient single-phase liquid systems, you get to avoid a lot of these hazards, and you get to save a lot of costs, reduce your valve cavitation, make sure that you can have proper startup, reduce equipment vibration, etc. Yeah. Okay. So this is another case. This is distributed blowdown. So again, I think most people are familiar with a lumped blowdown analyses that they typically have in HYSYS. This distributed case we'll get into. So this is for an FPSO system with a turret and a fuel gas import. Yeah, so in this case, they were importing fuel gas from another facility. Yeah, I can't remember how far it was. So if we take a look at FPSO, I think there's probably, if in Ghana, there's a lot of people working in the FPSO business, MODEC, Tullow, etc. And in this particular design, this has a turret. So this case, it's a rotating turret mooring system. So we have these swivels over here. So these swivels over here essentially provide an interface between the subsea pipes to the topside facility piping. Yeah. So what I'm going to look at is the fuel gas import line. So I've got the subsea pipeline coming in, the import line going up the riser through the swivel. So this would be one of those toruses. Yeah, so it's one of these toruses that you see here. And going through a superheater and through the fuel gas metering system and then into the fuel gas system. Yeah. So if you take a look at these are the design temperatures. So coming up from the gas riser, it's about the swivel has a design temperature of minus 30 degrees C. But everything after on the top side, after the heat exchanger, this is all like low temperature carbon steel. So it goes down to about minus 60. Yeah, now the minimum ambient temperature is about minus 8. So this was actually somewhere in the North Sea. If we take a look at the swivel structure is quite complex. You've got certain sections thicker, certain sections thinner. And, obviously this impacts a lot of the heat transfer. Yeah? So what people typically do, traditional depressuring, if you're an EPC company, if you've done any kind of depressuring, is you normally would lump this in a single volume. So you sum up all the volumes, add it to a volume, take a look at the thickness, figure out what is the most conservative thickness, and come up with a metal thickness over here and try to conserve the mass. So if you're using the tools in HYSYS or Unison, there's some fudge factors that you can put in to make sure that you conserve the mass. You can add on additional terms and various kinds of lumping tools, so you can lump all of the system here, all the piping, heat exchanger, tubing, etc., into a single volume. Yeah, which has a single mass transfer area and a single metal mass. So when the customer had actually done this analysis, and they found that everything was essentially settled out to ambient conditions. So it was a shutdown, and everything lined out to about 8 degrees Celsius. When they ran the traditional depressuring, the lumped depressuring, they found a minimum fluid temperature of minus 41 degrees Celsius. So this was a bit disconcerting. Obviously, the inner wall temperature may be higher than minus 41, but this was a bit disconcerting because it's just like a single lump. And you can see that thicknesses are going to vary across here. And if you lump everything together, you can't really tell where that low temperature spot is. If it's happening around here, I don't really care so much. But if somewhere around here, around the swivel, and this area, if I'm getting up minus 41, then I have some issues. So you can't find out where the cold spots are. You can't find out where you don't really know what the inner wall temperature is. So, it's difficult to determine whether all the points there are above the safety margin, above your design temperature. So what we did was we did a distributed blowdown analysis. So we actually built component by component in HYSYS. Now you're thinking, HYSYS dynamics, the native tools aren't really set up for rigorous heat transfer. But there's one thing that you need to understand in HYSYS. I'm not sure if you've used it, but each HYSYS object, the pipe objects, the stream objects, are actually programmable. You can customize them. You can actually treat HYSYS like a very expensive MathCAD. So using Visual Basic, we modified some of the heat transfer equations in the piping and the vessels to actually include rigorous heat transfer models. Yeah. So for convective heat transfer, free convection, forced convection, we'd added all of that detail inside. We'd also included a finite element analysis code to look at the wall thickness. So this is all customized. You're not going to find this in any of the commercial software. This is all written by myself and my team over here. So we have every single piece of piping in there, and the walls were modeled rigorously with our own code. Based on that, we can take a look at the temperatures, and then we can check the valve sizing as well. Yeah. Okay. So similar. Okay. If I take a look at this case, I take a look at the axial temperature profile across here. So I'm starting off at 0.123 all the way up to 8. I'm starting off at minus 8 degrees Celsius. So I have everything shut down, and I'm doing like an isochoric settle out at 8 degrees C. So I'm just letting the system, normal operations, shut it down, let everything equilibrate to 8 degrees C, let the pressure internally equilibrate as well. And let's take a look at what's happening. So I've got two graphs here. One is inner wall temperature, the other one is fluid temperature. And I'm calculating it for all of these points. Bear in mind, again, as I mentioned, it's using our own East 101 rigorous heat transfer routine. So the pressure start, you can see the depressuring starts. My liquid inventory temperature starts to drop, but the metal temperature still remains above because it's a thermal reservoir. It's still warm. Yeah, you've got the heat capacity of the metal. And you find that Well, this is the spot which looks like it's going down to about minus 41 at this point here, which is actually at this point here, around 4.4, 0.5. So this temperature is dropping to close to about 40, minus 40, but because there's a lot of metal mass around this point, because it's around the heater section, so the inner wall temperature is still pretty high. I don't have any issues there. And I'm seeing that over here. I have enough thermal mass to prevent the temperature from dropping too low. Yeah. So at this point where this is minus 30, I'm pretty safe. I'm way above like minus 20 over here. This point where it's minus 60 again, I'm pretty safe here as well. So now you've got some peace of mind. You know where the cold spots are. You don't have to, uh, you don't have to worry too much about having like any potential like cold spots or fatigue. Now, another thing that you want to do is to take a look at the cold area to find out the heat transfer across the wall. So for this, I wrote like a finite element method. HYSYS doesn't have finite element method, so this was our own code bolted into HYSYS. You can start off at minus 8. So I can see the heat transfer going across here. And I start the sim. So this is the fluid temperature dropping, but you can see the metal is still warm. Yeah. As you can see, the fluid starts removing more heat, and slowly this temperature gradient will start to reduce. And you can see that the outer wall also starts to drop. Now here's the interesting thing. So the outer wall is at minus 8 degrees C. So at some point in time, it starts absorbing heat from the wall, and you start seeing this temperature start to climb a little. Yeah. Now it's kind of dropping because of the rapid depressuring effect. Rapid temperature drop, but now at some point it'll start absorbing heat from the surrounding. You'll see this start to slow, and you'll see this temperature start to climb a bit. You can see yeah, so you can see everything start to come up a bit more. Yeah, so it stops about here. This temperature drops a bit, and then it blips up. Okay, so if we take a look at the distributed model, we find that we're pretty safe over here. Yeah, we don't have any issues. Swivel design temperature, these blue spots are all above, no problem, as well as further down. Okay. So we're able to put our customer's mind at ease with the system, with this distributed model as opposed to a lumped model. Okay. So let me run through the last one. This is for process safety time or a high integrity pressure protection system. So in this case, again, this is for an FPSO. So what happens is a lot of the piping around the transmission or the subsea lines are for a higher pressure rating compared to the top side. Yeah. So we normally have like a spec break over here. Sorry, a pressure rating break. Though obviously because your wellhead pressures are operating a lot higher. So in some cases, let's say if you had a shutdown and you restart the compressor, as you restart the your facility, sometimes what happens is within this riser, when you shut down, all the liquids will go to the lower points, and you'll find like a gas-packed riser. So this gas pack riser will be at a high pressure. When you start up your system, or if you open your valves over here, you might get a sudden pressure overpressure. Yeah, during when this riser starts to depack. So this computation is a bit more straightforward. So we take a look at the peak pressure developed in the worst case scenario. We want to find out how much time we have for the instrumented protection system, pressure protection system to activate. We want to know what the set points are, and we want to know what the minimum stroke time is for the instrumented pressure protection system valve is. If you have a HIPS valve, the normal stroke times are going to be about 3 or 4 minutes. Sorry, 3 or 4 seconds. Yeah. Okay, so in this case, we're looking at a slug catcher. The operating pressure is about 82 degrees C. Design pressure is about 101. MAW, the MAP, minimum allowable pressure, is going to be about 110 degrees above design. Margin is about 5% below MAP. Yeah. So the target, we want to make sure that this doesn't go about, you don't have an issue over here about 105.5. Yeah. So this is the system at early life. So GOR is about 1400. Gas is about like 85 million scuff. Liquids about 24,000 barrels. We want to know for this, what's the hip set point? Later life, we have higher GOR, higher gas flow. So obviously, when you're taking on these kinds of systems, your pressure is transmitted by gas. So the more gas you have, the faster your pressure, the system is going to pressurize. Yeah. So we're taking, in this particular case, we're looking at a sudden closure of the discharge. So we've done these analyses for early life and late life. And what we have here now is the pressure response of the system at the header and the vessel for each one of these systems. Yeah. So our target pressure is here for this. Yeah, about 105. So based on this, we were able to, you can see over here, without the hips, you can potentially get overpressure fairly within the 20 seconds or so. Actually, the simulation here started at about, I think it started about 10 seconds. Yeah, it started about 10 seconds to sim. So within about 10 seconds, you can get overpressure really quickly. Yeah. So again, having using the hips, there's two main issues, two main design issues that they're addressed. One is what is the safety time? How long do I have in order for this valve to react? And another thing that we determined is to determine what is the accurate set point. Because if we put the set point too low, you might get spurious trips, yeah, in the system. So yeah, that's all that I have. I thank you for your patience. I hope you managed to get a rough idea or some appreciation for some of the types of problems that one can address using dynamic simulation. So in this example, I had two different types of simulation. One is the HYSYS or flowsheet simulator type, where you typically use for gas-dominated systems, topside facility gas-dominated systems, or mixed phase systems where you have enough compressibility in the system, where momentum effects aren't really that governing, and liquid-based systems where you use something like PipeNet, where you're concerned about momentum. Yeah. So that's all I have. And again, I thank you. Perhaps you can go to the Q&A session.
Yes, we will move to the Q&A section. And thank you very much for the excellent delivery. So we have some few questions there. If you've not typed your question, kindly type your question. So I'll start. First come, first serve. So the first question is, when you have an HC gas in your CM system, it tells you the tubes of the coolers are leaking. Quick troubleshooting of individual coolers can tell which is leaking. Can the leaking tube in long run lead to a rupture? If so, how long can you run the system before changing, considering the fact that these coolers can take time to manufacture if there is no spare available for replacement?
Okay.
That
Thank you very
is the
much. I think this
first.
is coming from Joel.
Yes, from Joel.
Okay. I think for something like this, it really depends. Um, I think I don't think it's possible to come up with like a generalization for this. I think it would depend on the material and from the manufacturer. I'm probably not going to give you anything. I'm probably not going to give be able to make any useful or erudite um, recommendations here, because I if you've got a leaking tube, how long is it going to take to lead to a rupture? I think it really depends on your materials, the location of the leak and the operations of the system. So I'm afraid I really wouldn't have any idea of how this would what this would take. I think this is something that one would have uh, to address with the manufacturer. Yeah. Sorry, Joel. I'm afraid I can't give you anything more useful from that. I don't think it's something that I can predict or I understand. I don't really have any experience in predicting anything like this.
Okay. The next question is there a book to learn VBA customization of Hisense simulation?
That's a simple question. That's a simple answer. Uh, the answer for that is no. I don't see any commercial books out there. There is, if you look in the manual, there is like a VBA tutorial manual, which isn't really that um, comprehensive. When I learned VBA, and this was back when I learned the HISIS VBA back in the 90s, it was all by trial and error. And the best way I found to learn VBA was VBA for HISIS was first to learn VBA. So if you want to learn VBA or VB, there's a lot of books that have like a VB syntax, coding structure, architecture, and things like that. But getting used to the HISIS objects, the best way to do that would be to go to the Aspen or Honeywell site and try and download example codes and reverse engineer the codes. That's how I learned all of my VBA. That's how I learned all of my Fortran, C, C++, Pascal programming. I get familiar with some of the syntax and then reverse engineer everyone's codes. So unfortunately, Khalid, they don't really have any uh, books, commercial books. But if you're a HISIS or Aspen subscriber or Honeywell subscriber, the manuals, there is a VBA. They call it automation manual, but it's not very good. Yeah. If you have any, the best way again is go and try and find some programs, some of the VBA program. If you go to the support site, I think they have like a lot of VBA programs over there, HISIS VBA programs. Just download those and then you're going to have to kind of reverse engineer. Yeah.
Okay, thank you. The next question is from Nicholas Steven Spence. On many FPSO, vibration is an issue on seawater system, particularly with GRE and FRP piping. Can East 101 perform FIV steady stroke screening followed by FEA with simulation to identify which lines would require extra support to mitigate the vibration?
Okay. Thank you very much for your question, Nicholas. East on one, we primarily do the analysis that we do typically are on the fluid side. Most of us, all of us are actually process engineers and chemical engineers. So a lot of what we do tends to be on the fluid side. For the piping side, for the flow-induced vibration types of studies, we have a partner that we typically work with for that. So they handle all the FIV and FEA, and sometimes we will work together. We'd essentially provide all of the unbalanced force details that we get from the fluid side analyses, liquid surge, water hammer, and then we would provide those profiles for our partners to do a FIV or like the Caesar kinds of analyses. Yeah. But if you've got any current urgent requests, you can just contact either ourselves or Ebenezer. I've got the emails up there. If you're coming in from Ghana, please contact. You can contact Ebenezer and EBL. Anywhere outside of Ghana, you can just shoot something to sales@east101.com.
Okay. Please, is there any further questions? And I guess we should be wrapping up.
Okay. Well, I'd like to thank
So,
everyone.
So as we wrap up, we will first need to thank you once again for sharing your expertise to all of us and then everyone participating. And I would want to give a quick information here that we still want to remind you on the 2 week simulation training program. Instead of moving your team all the way to Malaysia, we will bring Raphael here for 2 weeks. If you are interested in both steady state and dynamic, you would let me know. If you are interested in just one of them, you can just participate in one of them. We are targeting between first quarter of 2026.
Yeah,
And
and if anyone wants to come to
one of
Malaysia, we happy to have you in Malaysia as well.
yeah, and one of our East 101 associate will be in Ghana on 24th of November
The week of
for
24th.
yes.
Yeah, one of our associates, a good friend of mine, is going to be there for. I think he's doing some project meetings. So uh, I think I've told him to go and pay some visits. Maybe talk a bit about some of the services that we do. His area of expertise is safety, so he's like a safety guy. He does all the HAZOPs, SIL, and all that. So if anyone's available, maybe just let Ebenezer know, and he can come by and maybe have a quick chat about some of the stuff that we do. Sorry, Ebenezer, I kind of interrupted you.
Yeah, not really. I'm trying to drop my email on the chat, and basically those are the two information I wanted to relay. So specifically the upcoming training. So once we know the numbers, that would assist us to organize. So please, you can contact me directly on my email or my phone number that I'm dropping it in the chat.
Is it in the chat already? Or you're putting it there?
I just drop it.
Okay. Hasn't appeared for me yet. Ah, there it is. Oh, yeah. Okay, sounds good. I really hope we can get the training going. It was really I had a really good time before. That was the first time that I'd ever been to Ghana, or actually I'd set foot on the African continent. So it was really interesting. Like environment-wise, it was almost like Malaysia. So I think some of you, I think Nana, you've been over here before. You'll see like palm oil and stuff, palm oil trees, and a lot of similar foliage over here. So it's always fun to go back there. I really hope we manage to do something for training.
Okay. All right. So as we stated, for the participant to get like a full benefit, we limit the training to a maximum of 25. So if you are interested, please let us know so that we can reserve your seat. Once again, thank you very much for your time for this section, Raphael, and to all the participants. So we look forward to see you in our future webinar and the trainings. Thank you once again.
Okay,
Have
thank
a
you all.
wonderful
Everyone
day.
have a great day and have a great weekend.
Thank you.
Thank you.